Yes, I wasn't talking because it wasn't 12 o'clock yet, or at least according to my watch. But now it is 12 o'clock noon. Welcome to Computer Organization Lecture 14, if I counted correctly. So we are officially in the second half of the semester. Halfway done. Isn't that great? All right, welcome everybody. Good afternoon, and hopefully you're in good spirits. The weather it's kind of cold, but it's sunny here in Troy. So hopefully we have all our panelists in place and ready to answer questions. So I can see already a test question appeared, but yeah, please remember it's a test question. It's not the real thing, right? So there will be no emphasis on C coding in this upcoming test. Okay, so let's get started. Let me start sharing something with you folks. Well, I wouldn't say let's go no C. You will have to do more C in the future in this class, but it's just not going to be the emphasis. All right, and let me organize my windows. Will global pointers or GP be on the exam? Yes. So GP, SP, FP, this relates to the topic of segments, memory segments, segmentation of memory. And yes, this is a topic that was not included in the previous test, so it will be included in this one. Did we do K-maps in this class already? No, we are doing it today. All right, so let's get started with my agenda. All right, homework 3 being graded. So we barely started, but we are on it. And then homework 4 was posted. I know some folks already started working on that homework, despite the fact that it won't be due until next week. And just remember that we are back to our Tuesday homework deadline schedule. So homework 4 will be due on Tuesday next week. So we kind of, we had some extensions, but now we should get back on track with homework being due on Tuesdays. And in Zybooks, what does COD mean? COD is the short name of our textbook, Computer Organization and Design. That is the colloquial. That is a well-known actually name in industry for our. Yeah, it's not Call of Duty for our textbook. So it's many very well-known textbooks have their colloquial, very known names like COD. Is Computer Organization Design, and if you take PSoft, you will hear about their book that is known as the Gang of Four because it was written by 4 dudes. So it's also a well-known book that goes by Gang of Four book, GOF. Okay, so it's pretty common. All right, and so homework 4 for the first time in a while that there is no coding. So just textbook style problems, and actually only one of them is from the textbook, and the rest are the same kind of style, but not from our textbook. Yeah, no coding for this one. There will be a lot more C coding coming up, so just get yourself ready, but take a little bit of rest from writing C code. On this assignment. All right, so as I mentioned, some people already started working on homework 4, and I think that's a great idea. Especially someone mentioned to me that Fox midterms are coming up, so it would be great if you could get done with homework 4, and not have it in a way of your preparation for Fox exams. Okay, and so then, exam 3, I almost released the grades. So we are done grading, but then I noticed something that, turned out to be a slight imperfection in grading, so we have to fix it. Don't worry, it is only going to increase the grade. So I noticed a deduction which was not, which looked like it wasn't properly applied, and the TA who graded that question agreed that yes, that deduction should be removed. So as soon as they remove that deduction, we will post the grades. And solutions are already posted, so you can review them for exam 3, and I'm hoping that we will release exam 3 grades, and I will make an announcement. So the results are actually very, 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 very strong, and we are going to have one student, one person, at least one. I know maybe there's more, but there is one student who scored a perfect 100 out of 100. Well, 100 out of 80, right? Because we made problem 6 optional next to credit, but that person did all 6 problems and earned 100. Okay, never lost a single point. So that's truly remarkable. And if that person wishes to identify themselves, I'm more than willing to say their name. But if they want to remain anonymous, of course, it's their choice. But I was genuinely impressed. Okay, so yeah, and it's 125%, and we don't cap their extra credit. So if that person lost any points on anything else, like on any of the previous exams, this extra credit that they earned on test 3 would make up for any points they lost anywhere else. Actually, about 15% of the class, if not more. So 15% was when I looked before this final adjustment that we are doing right now. But at least 15% of the class went over 80. So they are above 100% on this test 3. So I think that's also a very, very strong result. Think we should have extra credit on every exam? Well, I don't know. My TAs are not particularly happy about that because they have to grade more. But yeah, we are thinking about what can be done to this class is hard. No doubt about it. But we were trying to make it not depressing for most students, and at least have students who invest their time in this class and do their due diligence and solve practice problems and prepare for exams. We want to make sure that these students get good grades. Okay, but yeah, the material is hard, and there's not much we can do about it, right? Because we have the syllabus and the material that we have to cover. All right, so for exam 4, our test 4 that is coming up tomorrow. So we already discussed the scope of the test on submitted forum. So it's MIPS procedures and everything that goes along with that last topic from the previous chapter 2. So segments, all those GP, FP, SP, saving stuff on stack, and just in general using stack, and then calling conventions for procedures. So how do you pass the arguments? How do you pass the return value? What do you do if you have more arguments to pass than 4? And calling conventions regarding saving the registers, like do we save T registers? Do we save S registers? Do we save it on the caller side? Do we save it on the callee side? So all those questions. So chapter 3A, the first part of chapter 3, which if you look at the textbook, includes mostly appendix B and some of the contents from chapter 3. But if you look at their slides, so slides are labeled 3A. So everything that we've covered so far, Boolean algebra, axioms and laws of Boolean algebra, using those, applying those rules and the axioms to simplify Boolean expressions, and then logic gates, and then digital components. And we will go over a couple more today, and then SOP and POS forms of Boolean expressions, and then finally K-maps. So even if we start ALU today, it's not going to be on their test. On this test, it's going to be on their next test, on the following test, of course, right? So ALU is not going to be on the upcoming test. And I think someone is not muted. but I cannot see who. Okay. Yeah, sum of products and products of sum. Okay, so practice problems have been posted for exam 4, and this morning I posted the solutions. So please don't look in the solutions if you didn't have a chance to solve the problems yourself. As I mentioned multiple times, it is a lot more advantageous to you to actually solve the problems than just compare the answers, rather than just look at the solutions without really doing all the work. Okay, it's not the same experience. So, but the solutions are there if you need them. And there's this additional file that has been posted a few days ago, I think on Friday, with additional practice problems on Boolean laws and all this stuff. So I have this file open here, bool.txt. So those are problems with some examples, with example solutions. And note that quite often there is more than one solution. So this is perfectly normal. Okay. And when a common question is, when do you know, like if we give you an expression and ask you to simplify this expression by using their laws and axioms and of Boolean algebra, like how do you know when to stop? And the answer is you stop when you cannot apply any of the laws or any of the axioms. Okay, so if you still can apply something to make this expression simpler, then you should keep going. And on their exam, when we give you an expression and ask you to simplify, we assume that you will simplify it all the way until there's absolutely nothing else that you can apply. Okay, if you stop halfway through the process, then you're only going to get partial credit. All right, so we are clear on that. Yeah, go ahead.
Hi, I got an email that says I'm a panelist today, but I don't have the co-host role.
Okay, let me add you. Can you? All right. What is? Can you put your name in the chat so that I can?
Yeah, sure.
Find you. Okay.
Yeah.
Got it. And
Thank you.
you're welcome. Well, wait until it works. Okay. You should be all set now for being a panelist today. All right. Can we derive our own laws and use them multiple times? Yes, you can. But you have to show the derivation of your law, and then of course you can apply the result. Okay, so bool.txt, please take a look at it as another example. And at the request of several students, we ran a poll, a submittee poll on running another Q&A session like we did before the previous test, and there were quite a few students who voted in favor, and it looks like their time that most people voted for, the time that had most votes, was tonight 8 p.m. So we will have a Q&A session again on Webex at 8 p.m. tonight for the upcoming test. So please, it's a student question-driven session, so please come with your questions. Otherwise, I wouldn't know what to talk about. Okay, so come with your questions, and if you need me to come up with some additional examples, we don't have much time left, but if you want me to come up with some additional examples, please let me know as soon as you can. I don't promise, but if I have time today, I will try to write out those examples. Yes, and some students mentioned that last Q&A session, they didn't even know it was offered. I don't know what might have happened, but when I make an announcement on Submittee forum, I usually put a checkbox, and that announcement is sent by email to the entire class. So at least hopefully this time, everyone should have received a message from Submittee forum with this announcement for their session tonight. All right. So why are reviews problems so late? Well, because we only cover the material. We only have 2 weeks between their exams. Okay, so I cannot post the review problems for the material that we haven't even covered. Okay, and depending on our pace and the number of questions and all the variables that are very hard to predict in advance. We don't even know how much material we're gonna exactly cover in the next couple of weeks. Okay, so but you should be able to actually. So again, someone asked me about like what are other resources that people could use to prepare for the exams, and exercises at the end of the textbook, which also exist in Zybooks, I think is a great resource. And I don't know if any of you actually noticed on test 3, one of their questions was directly from their exercises chapter in the textbook. Okay, so where I'm going with this is if you actually solved all those exercises at the end of their chapter, you would have a very easy time with the exam, because basically you would know what the answer is because you would have solved it already. Yeah, it was the processor one. Exactly. Yep. Yeah, some people were confused about the wording of that question. I was like, well, folks, I didn't even write that question. So, it's Hennish and Pedersen that wrote that actual question. So, they are very known, very respected computer scientists and computer engineers, and they for them English is a native language. So I don't know if it was if it was not properly worded, then I don't know how we could make that better. Okay, because that was actually a problem from the textbook. All right. So now let's get back to our business and talk about slides. Oh, one more thing before we do that. So drop deadline is this Friday, 10/22. Okay, if you are contemplating about dropping this class, please make sure that you do that by Friday. Of course, I am not encouraging anyone to do that, but if you think it would be beneficial for you for whatever reason, so I just wanted to remind you about the official drop deadline. All right, and now we need to get back to our problems that our topics that we need to talk about today. All right, and we left off talking about the not here. About decoders. And we talked about 2 input decoders, and then we had a 3 input decoder. And of course, you can expand it further, so you can build a 4 input decoder. So there are different ways to actually build all those components. And you probably should expect a question related to those digital components on their upcoming test. And questions may vary from something like, please implement this digital component, to something like, oh, we give you these parts and we ask you to build another digital component just using the parts that we give you. And if you think about the practice problems, so let me actually go to our practice problems for this exam. I believe one of the problems was exactly like that. Yes, so it was a 2-part question, question number 9. So first you were asked to build a 2 decoder with a slight modification, this additional enable input signal. And then you were asked to use that 2 decoder with enable to construct a faux decoder, right? But using no AND or gates. So just using their 2 decoder with enable. Okay, so Something like that is very likely to appear on their test again, right? Because you need to be able to synthesize, to build components using the existing components, using the components that we reviewed, or using the components that are given to you as building blocks, as bricks. Okay, so that is a very, very important skill. All right, so for the 3-input decoder, we can just approach it in a straightforward manner and just build a truth table. All decoders work the same way. The principle is the same. The output is exactly only one output is asserted at a time, and that output corresponds to the binary value of the inputs. So if the binary value of so if my inputs are 0, 1, 1, so it's 3, and if we treat those inputs as a binary number, and then O3 is asserted. Okay, and we mentioned that asserted means set to 1, deasserted means set to 0. So we can then just decode, as far as implementation is concerned, we can just write Boolean expressions for each of the outputs. So we're going to have 8 functions, and then we can just implement them in a straightforward manner with their and or gates. We don't need any or gates here, so just and gates and not gates, negation. But this is just a straightforward approach. Of course, it's going to be a little tedious if you were asked to actually draw that circuit, because that would be a lot of gates. And you can imagine it would be even more gates if we asked you for a 4 decoder, because for a 3 decoder there are 8 outputs. For 4 decoder there would be 16 outputs and so forth. So think about 5 decoder or 6 decoder. Okay, that would be a lot of gates. And for that reason, it is very attractive. It is very you would really want to reuse existing components to build like higher order components. Like, can you think of a way to build, let's say, a 3 decoder using a 2 decoder? So those kinds of questions are very important. And it turns out that you usually are able to do something like that, maybe with slight modifications. Like with a decoder, you actually need to have a decoder with the enable signal to do that, right? And enable signal is just something that turns off the entire output of the decoder, right? A regular encoder without enable, you always have one of the outputs asserted, as you can see from this truth table, right? So if we are building higher order decoders using 2 decoders or 3 decoders, that kind of prevents us from actually doing this. So we want a decoder that we can switch off outputs off. Okay, so we can a decoder where we could deassert all outputs. And this is exactly the meaning of the enable signal. If the decoder is not enabled, all outputs are at 0. If the decoder is enabled, then their output, exactly one output is asserted depending on their inputs. Okay, so that's the meaning of that input signal that we call E, or enabled. And it's just an input signal, so it's 0 or 1. 1 means it's enabled, 0 means it's not enabled, that is, it is disabled. Will we ever get to 4 to 16 decoders? Well, you had to build a 4 decoder as an exercise, okay, as this practice problem. So, and the solutions have been posted, so you can verify your answers. Okay, what is a decoder exactly? We discussed this last time, so please review the slides from there that we covered in the previous lecture. If we have time, I can explain it again, but for now, let's just move on. All right, so there is a small digression that we have to make, that we have to discuss when discussing implementing different digital components. So far, we have seen gates like AND gate and OR gate with just 2 inputs. which was just a straightforward implementation of their corresponding Boolean functions with 2 arguments. And that is sometimes not very convenient, because what if I have to AND 3 arguments? So what if I have to implement A and B and C? So we can still use our traditional 2 input gates, but we have to organize them in several levels. Okay, so we have to do this layered implementation where we first do A and B, and then we AND that result with C. So that would require 2 gates, two input gates, and this is totally possible, but it would be, of course, a lot more convenient if we had a 3 input gate available to us. Okay, and so there are gates with more than 2 inputs, so this is quite common. But please, in problems like homework problems, exam problems, please pay attention to what we tell you you can or cannot use. We might tell you that you can only use 2 input gates, or we may say you may use gates with as many inputs as you can. Or we can say, well, you can use gates, but up to 4 gates, up to 4 inputs. So that is important, because do not always assume that you have access to gates with multiple inputs. The important consequence that we will also talk in more detail later is their latency. So each gate, and any electronic circle, any electronic circuit is not, does not have infinite performance, does not have infinite speed. So all signals propagate with a certain finite speed, or we can quantify that speed as latency. So for example, if at time 0 you supply your input signals to A and B, then their output signal will not appear at that same moment of time to 0. It will appear with a certain delay that is called latency. Okay, and that delay is determined by the components that comprise this gate, right? What those components and how fast they can switch, and that determines their, the speed of that component, and it's in any case not 0. So if at time 0 you supply A and B, then maybe the output will get the correct output value in, let's say 10 nanoseconds. Okay, it's a small amount of time, but it's still not 0. And so if you cascade your gates, like in this example, you can see that their latency will be summed. Okay, the latency will be accumulated, because there's a latency that the first gate introduces, and then the second gate, since it is connected in series, right? It is connected, in a chained manner. The second gate will add its own latency. So the actual output will appear after 2 gate latencies, not just 1. Okay, and that is important when we will be talking about the latencies and overall synchronization of digital circuits. Whereas if you have a 3 input gate, then of course it only introduces 1 latency, right? The latency of that single gate. All right, so that's that. As far as our Boolean algebra is concerned, we can easily do those cascaded circuits, right? Because of the associative property of Boolean algebra. All right, so this is our revised partial 3 decoder, right? Partial because we just, it's just going to be a lot of additional gates for all the 8 outputs. So that's that. Just the difference, once again, to highlight, is that we no longer have to use, we are no longer limited to 2 input gates, which we had to cascade previously, like as you can see here. And I can actually, so here we had to cascade 2 input gates, and here, if we have access to a 3 input gate, we just replace these 2 with 1, and that's it. Okay, so a 3 decoder uses 2 input AND gates or 3 input AND gates or both. Well, not both, but depending on the hardware that is available to you, it may use one or the other. It depends on how exactly you implement your 3 decoder. In realistic settings, in the practical world, you will most likely be implementing decoders as part of the programmable logic circuit, PLC, or FPGA or PLD. There are different names. They're slightly different. And if you're interested, you can read the textbook. We're not gonna talk about them, unfortunately, in this class. Because we just don't have time. But if you're using any of those programmable devices, usually you have like a grid of input signals that you can connect pretty much arbitrarily, and that essentially gives you the ability to have gates with as many inputs as you have input signals. So, like if you have 200 inputs, you can have an AND gate with 200 inputs, right? So that you can, combine all your input signals, all your input pins with a single AND gate if you need to. All right, and so of course the same applies to OR gates. So you can cascade them if you need more than 2 inputs and you only have access to 2 input gates, but you can also replace them if you have access to gates with more than 2 inputs. You can replace them with 3 input gates or 4 input gates. And if you're drawing your circuits with open circuits, then you can configure your gates to the number of inputs that you need. And I think the limit there is 8. So open circuit supports up to 8 inputs per gate currently. By the way, speaking about open circuits, last lecture I mentioned that there are features of downloading your circuit diagram as a PNG or a PDF was not working. And guess what? Some of the people who are on Open Circuits team are actually taking this class, so they are doing their best to actually make open circuits very convenient for this class. And so they fix bugs almost immediately, and they actually fixed that bug that same day on I think it was Friday. Okay, so now download PNG, download PDF works. So please use those features for your homework or just as you are playing with open circuits. Okay. So yeah, I was very impressed with with how quickly they responded to the open circuits team responded to our needs, and I'm very appreciative of that. All right, so here is the pop quiz. Okay, so basically it is about the topic that we just discussed. If we are only limited to 2 input AND gates, how many layers of gates, right, we would need to implement this function? So let me turn on this poll. Hopefully it's the right one. Please let me know if it is available and if it looks like the right poll. Okay, cool. And so we are back. All right, so next, a very important device or component that we need to talk about is a multiplexer. And if you can probably get away with and go through this course without really knowing what a decoder is or how it works, I mean you would probably lose points on on some exam or something. But largely we probably are not gonna see that many decoders in our future topics. Not to discount that that digital component decoder, it's still important, but what I'm getting at is multiplexer is something that you absolutely need to understand very well how this works, because pretty much all the diagrams that we will be reviewing in our next topic, the data path, when we look at the internals of a processor, each of those, except for maybe the simplest diagrams, but the vast majority of diagrams will have multiplexers. Okay, so multiplexer is a very important component for us. So let's please make sure that you understand how it works and what it does and why it is so useful. And if there are any questions, please ask. And as usual, panelists, if you come across a question that you do not know how to answer, but you feel that it's a very important question, please just unmute yourself and serve that question to me, because I am not, really tracking the status of our Q&A as I'm speaking. It's kind of hard to multitask, but if it's an important question that you feel should be answered, please serve it to me. Okay, so a multiplexer is a device that, of course, can take multiple forms, right? It shouldn't be a surprise for you based on the decoders, right? We had a 2 decoder, 3 decoder, 4 decoder, and so forth. So similarly, multiplexers can have different number of inputs. What is common for all multiplexers is they have only one output. Okay, so unlike a decoder, which has multiple outputs, and the more inputs the decoder had, the more output the decoder had, and it was actually exponential, right? The number of inputs was 2 to the power of the number of inputs. With a multiplexer, it's different. It always has one output, and it has a number of inputs. So in this case, it's 2 inputs, and that's why it's called a 2 multiplexer or 2 input multiplexer. But there is an additional input signal that is called S, or selector. Okay, selector. And selector, if I ask you to guess what selector does, you would say, well, selector must be selecting, and this is exactly so. Selector selects. What does it select? Selector selects which input signal will be connected to their output. So you can almost think of the selector as an electronically controlled switch. Okay, so we can kind of depict it like that. And then we put the dashed line here to indicate that this switch is controlled by their S signal. So if S is at 0, it means that our switch our switch is connected to the first input. Okay, so that means that whatever signal is on I0, it will be routed to the output like that. Okay, because S is at 0, so the output just repeats what is on I0. And of course, the opposite. Let me erase this. So if S is 1, then this switch is connected like that. Okay, and then it just routes I1 to the output. Okay, so it's like that. All right, so it's basically an electronically controlled switch. And as such, it is an extremely common component, because we quite often want to reroute our circuit based on the value of some also electronic signals, right? Not just hardware it once and forever, but have this circuit the ability to switch between something and something. So exactly as someone just noted in their chat, if you have more inputs, you're gonna have more selectors. So can someone tell me if we have a 4-input multiplexer, and multiplexer is often abbreviated as MUX, then how many input signals for the selector do we need to have? 2, exactly. So it will be 2 S signals, like S0, S1. So And now you can see the analogy between, well, not the analogy, but the contrast between their decoder and their multiplexer. For the decoder, their number of outputs is their 2 to the power of the number of inputs. It's the exponent. With the multiplexer, it's the logarithm, right? So we have the logarithm number of S inputs, S bits, selector bits, compared to the number of inputs. Yes, 3-input multiplexers exist because they are actually 4-input multiplexers. So let's actually look at this. So someone asked basically the question like, what if we need to have a multiplexer with 3 inputs? Okay, there's always only one output and 3 inputs, O0, O1, O2. Okay, so how many selector bits do we need to have? Well, we still have, we cannot go with just one. We have to have 2, all right? Because 1 would only allow us to select between 2 things, not 3 things. So we still need to have 4 of them, okay? 2 selector bits, okay? So that means that, if we look at all the selector bits and, the possible values, there are 4 values no matter how you slice it, right? Because there are just 4 combinations that you can get with 2 bits. And that means that it will be essentially a 4 multiplexer. So if you don't need that 4th, it's not O, sorry, it's of course I. And those are all I's. Right? If you don't need that 4th input, then just don't use it. Right? If you know that your selector bits will never gonna, it's I4, I3, I0, I1, I2, I3. Right? So if you don't use that I3, you don't have to use it. You can just set it to 0, for example, and make sure that your selector bits are never both ones. So that would be essentially your 3-input multiplexers. But as you can see, technically it's a 4-input multiplexer, so you can use it for 4 inputs if you need to. Well, 1 would not be undefined. Okay, so nothing would prevent someone from supplying 1 and 1 to the input of this multiplexer. Okay, so you have to account for that possibility. But if 1 and 1 is applied, then the output would be just 0, right? Because I3 is connected to 0 to false. Okay, so yes, you cannot. And if you want to prevent S0 and S1 both from being 1, you have to build additional circuitry that prevents this. That would be possible, right? So for example, can you build a circuit that given S0, S1 would produce S0 prime, S1 prime as, let's say, 0, 0. Okay? And then all others would be the same. Okay, so you can build such a circuit that if given 1 and 1, it just changes. It just produces the output of 0, 0. Okay, so that would be something along the lines how you would probably want to do it. All right. So that's that. And now let's actually look at the implementation of the 2 multiplexer. So the output depends on I not I1. The output also depends on S, and therefore we see that the function that describes our output signal must be a function of all input signals and all selector signals. And then we just follow the definition of a multiplexer to build a truth table. So whenever this selector is 0, right? So it's this part, selector is 0. We must ensure that the output is the same as I naught. And we just copy I naught part to the output, right? Because that means if I naught is 0, the output is 0. If I naught is 1, the output is 1 for S of 0. And in this, first half, we basically ignore what I1 is, right? We just go through all combinations of I1. I1 doesn't matter. And for S of 1, it's exactly the opposite. We have to ensure that whatever is on our I1 input is also on our output. So we just do that and we ignore I0. All right, so this is their abbreviated truth table on the left, right? But it is, it is shorter. It is convenient to kind of grasp the meaning. Oh, if S is 0, the output is I naught. If S is 1, the output is I1. But for the actual implementation in gates, we need to expand it to the full truth table, which for 3 inputs is going to have 8 rows. Okay, and once we have the truth table, then we just implement it using our gates as usual, and we can optionally rewrite this as this expression, okay, using just 2 terms. And since S cannot be both 1 and 0, it guarantees that only one of the terms can be a 1. All right, and someone is asking about moving test 4 to another week. Unfortunately, that's not possible because we have that room reserved for us only on specific dates, and that dates have been fixed. Other weeks on Wednesdays, that room is given to some other classes to hold their exams. So unfortunately, there's no way we can reschedule tests. All right, so this is our logic design for 2 multiplexer, so 2 AND gates and 1 OR gate. Yeah, it would be, back to the exam rescheduling. It would give us a lot more freedom and flexibility, but unfortunately, the situation with rooms at RPI is very difficult. All right, so for input multiplexer, we basically described it already, right? So this is the abbreviated truth table. We have 4 inputs right here, and then there, if you think about it, the binary value of the selector determines the number of the input that will be routed to the output. So, if we are here, it's basically number 2, 1, 0, and then it's going to be their second input connected to the output. Right? Be careful a little bit when interpreting their signals as binary values, because like here in this slide, you can see that it's a little unnatural to see S0 to the left of S1. So it's more common to have something like S4, S3, S2, S1, S0 written like that, right? So that S0 is kind of assumed to be their least significant if we treat this as a number. But it's just a convention. Okay, so by themselves, those signals are not numbers. They're just individual signals, and you should treat them as such. If you want to treat them as binary numbers, then be careful about how you place, how you assign weights. Do you treat S0 as the signal with the lowest weight, the least significant bit, or with the highest weight, their most significant weight? Is it normal to take tests before labs and homeworks in this class? Well, we covered all the material, and we are finishing this material today that you will need for the test. So it is normal to have tests on any material that was covered, right? So we, unfortunately, given their schedule, we cannot have, first study the material 2 weeks, then 1 week later have a lab, then 2 weeks later have homework, and then 2 more weeks later have an exam, right? There's no way we could schedule, things like that in this class with 7 exams, okay? So exams are based on the material that we learned in lectures. All right, so here's another possible 4 multiplexer. So you can see you can actually use a decoder to simplify the design of a 4 multiplexer. You could totally do a 4 multiplexer with just the gates as we did with a 2 multiplexer, but it would be a little more complicated design, as you can see. So we could save us a little bit of time if we reuse the existing components, the components that we have already covered. So for example, a 2 decoder, right, very conveniently does exactly what we want. It decodes our selector signals by activating exactly one of the outputs, and then we can use that output to decide which of the I signals, I inputs, would be routed to the output. Okay, because whichever output of the decoder has a 1, it means that all other outputs would have zeros. And we have AND gates. So for AND gates, if one input is 0, it means the output would be guaranteed 0. And that means that this output here, all right, it has one input as 1, so it logically doesn't matter, which means that the output will be determined by this input here. If I1 is 1, then the output would be 1. If I1 is 0, then the output would be 0. So basically the output just repeats I1, and then we have 0, I1, 0, 0, so the output would be I1, exactly what we need. I think what David meant, swapping the homework and exam dates, not making exams every 4 weeks. Well, like I said, exam dates, we cannot really move them. Okay, so we have more flexibility with homework assignments. Okay, so we can move the deadline for the homework earlier, but note that the homework includes the material that we have not yet covered. Okay, but we will cover, like the so some of the topics that are on the homework are actually something that we will cover next time. Okay. And you can totally do the homework material before the upcoming test. Just the material that we covered. That I think is also true. All right. So this slide, explain it again. Sure. So the decoder would have their exactly one output, right? So those are 4 outputs of the decoder activated. It's a decoder, therefore, if S0 is 1, S1 is 0, okay? So that means that this output here, right? This output will be 1, and all other outputs would be zeros, okay? And then that single output that is 1 determines which of the I signals will pass through the corresponding AND gate, right? This is an AND. So if one input of an AND is 1, it means that it doesn't matter, okay, for the output. It means that the output of this AND gate will be determined by the second input of this AND gate, right? Because 1 AND something, right? So we can write 1 AND I1, okay? It will be 1 if I1 is 1. If I1 is 1, and let's call this, I don't know, P, right? So this is P. So, okay. So if I1 is 1, it's 1 and 1. The P is 1. If I1 is 0, 0 and 1 is 0. Okay, so we see that P is exactly I1. Okay. So that's how, that's why we write I1 as the output here. And then since all other AND gates output as 0, that means that this OR gate will always have exactly one non, it will have 3 0 inputs and 1 which is repeating their input, this I1. Okay. All right. So that was their multiplexer. And then common implementations of Boolean expressions. That's where things get really interesting. We have seen that we could build a truth table for something, right? For some component that we are trying to make, like this one, and then we need to transition from the truth table to the implementation using gates. And so far, I was kind of waving my hands. I don't know if you noticed or not, by not explaining how exactly this is done. Okay? Because in some cases it is intuitive, like we can write an expression, something like that, just based of the description of the component, and then implement it. But it's just one case, and if you want a general approach, we need to have something else. We need to have some kind of more disciplined approach on how to convert a truth table to the actual implementation with gates. All right, and the way to do it, there's actually more than one. So there are methods, two methods. One of them is called product of sums. Another one is called sum of products. So these methods allow you to, pretty much mechanically convert a truth table to an implementation with the basis that you're using, and we are using and or not gates as our functional basis. So that would be our basis for now. Right, so what is product of sums? Well, as the name suggests, it's a product of sums. Sum is or, product is and. So first we need to mention that it's a two-layer circuit. The first layer would be sums, would be OR gates, right? Because it's of sums, so sums are ORs. And then all of those intermediate results of all the outputs of OR gates will be connected together by a product, by an AND gate. And if we have unlimited number of inputs, there we will only need one AND gate. Sum of products is kind of the opposite. So we have products, so we have AND gates, and then we have a sum of them. So we have a single OR gate at the second level, so it's a cascaded circuit. So we have an OR gate that would combine the outputs of all those ANDs. Okay. So let's talk about these two methods in more detail and look at how we can actually do that. So for the sum of products, we first have to express the function by listing all the combinations from the truth table where output is 1. And then we only look at those rows for which the function is 1, and we represent each combination of inputs in that row with an AND gate. And then last step, we OR the results of all those AND gates in the first layer. So OR gate would be the second layer, AND gates will be the first layer. So we OR all the results of our first layer gates, our AND gates. And the example is right here to make things clearer. So imagine you are given a function with this kind of truth table. So we are trying to construct the circuitry that would implement this truth table. So intuitively, hopefully it's clear that, well, we just have to make sure that our circuit produces ones for those rows, right, where we have ones. And that would kind of mean that for all other combinations of inputs, it would produce 0, right? Because we only have two values, zeros and ones. So whenever the output of our circuit is not 0, it invariably will be, is not 1, it invariably will be 0. So we don't have to worry about zeros, right? We have to worry about ones. And we make sure that when our function is 1, our circuit produces ones, and all other combinations will be zeros. All right, and the way you do it, so if you want for these inputs right here, if you want their output to be 1, and you are allowed to use only AND gates, right? Because it's a sum of products. So it's a product, right? This has to be a product. So how do you, so this is my 3-input AND gate, right? That I want to produce 1 out of the values of S, I naught, and I1. Okay, so for this row, it means that, well, I have to negate S so that it is 1. I have to take I naught straight, and I have to take I1 negated so that I have all ones here, and that is the only combination that guarantees the 1 at the output. Okay, so 1, 1, and 1, that's what I need. So that means that if the input is at 0 for this row, I have to invert it. Okay, so this is exactly what is spelled out in the slide. If S is 1 in that row, connect S to a 3-input gate. Otherwise, connect not S, right? S with an overbar. And do the same for I naught and I1. And then do that for all the other rows that have ones. Okay, so we have 4 of them, so we will need 4 AND gates, and then we will just connect the outputs to this OR gate, and that would be our O. Okay, so POS and SOP are just methods that allow you to kind of mechanically just following a procedure without really thinking much. You just need to know how this is done. You don't really have to think a lot to implement any any Boolean function that that has a truth table, right? So if you have a truth table, you can just apply this mechanically and get an implementation. This implementation is not guaranteed to be minimal. It is not guaranteed to have a minimal number of gates, but this procedure is simple, right? Minimization is the next step, which we are getting into. All right. So with SOP, this is how it is done, and this is what we've done on the previous slide, right? So if we take another row, this row, right, then we see that S is 1, so we don't invert it. I naught is 0, so we have to invert it. And that I1 is 1, so we take it straight. We don't invert it. Okay. So that's the construction of circuit using their SOP approach. And of course, you can express it not just as a circuit, but as a Boolean expression as well, right? So we would have something like not S and I naught and not I1 plus, and then for the second row it would be not S and I naught and I1 plus or, and then the third row would be S and not I naught and I1, and finally for the third it would be S, I naught, and I1. Okay, so that would be the sum of products. You see, it is really a sum, all those pluses, of products, right? Each term is a product. So we can write it as a formula, we can implement it as a circuit. Just to summarize, for each row in the truth table where the function, the output is 1, we build the corresponding AND gates, right, for each row, 1 gate, and we ignore all the rows where the function is 0, right? We're gonna get this for free. We don't have to worry about that. And then we connect the outputs of all those AND gates to one big OR gate if we have one available. If we only have 2 input OR gates, of course, we just do cascaded circuit as we did before. All right, so that's the sum of products. And we can just spot check to make sure that zero values of the function are are correctly given. So for example, let's look at this combination. All inputs are zeros, and then we can go through our formula and check that each term, each product is going to be a zero. Okay, I naught is zero, so so this one is zero. I naught is zero, this one is zero. Here I1 is 0, so this one is 0. Here S is 0, so this term is 0, right? So for this first row, we verified that all 4 terms are zeros, given that all inputs are zeros, and therefore we have an OR of 4 zeros in the second layer, and the output of the function is 0 as it should be. So we didn't have to worry about it. It kind of makes itself automatically. That's the SOP. All right, so here is our multiplexer, two multiplexer as a sum of products, just based off the truth table that we reviewed before. And yeah, exactly, you see, we have as many, so we only have one gate here, right? If we assuming that we have access to gates with as many inputs as we need, and we have as many AND gates as we have number of ones in our output. Okay, we have 4 rows with ones, we have 4 gates. Each gate has how many inputs? As many inputs as we have inputs to our component, 3. So we need 3 input AND gates, and then we just go through each row, and if the variable is 0, we negate it. If the variable is 1, we take it straight, and I1 is 0, so we negate it, and that's it. All right, continuing. Oh, pop quiz, number 2. All right, and we are continuing. All right, so here's the product of sums. All right, so the second method, conceptually very similar to sum of products, except for, you kind of swap it. So you express the function by listing all combinations of inputs where the output should be 0. So you are trying to cover 0 cases, and then you will get all ones kind of for free automatically if you follow this procedure. And for those rows that have 0 as their function, as the output, we look at their rows, and we put all inputs, negated or straight, depending on their values, to their OR gate. Okay, because we have a product of sums. Sum is an OR. Okay, so first layer is OR gates, and then we have a product of them. So we have an AND gate as their second layer. All right, so let's do the same multiplexer to multiplexer, same truth table, but now for the product of sums. So we have those shaded gray, with gray background rows. Those are the ones that have zeros as the output. So we only worry about them for the POS. And if if an input is 0, we connect it straight to the OR gate. And if their input is 1, we negate it. Okay. So if we look at the first row, we have an OR gate, and we have 3 inputs. And if S is 0 in that row, connect S directly without negation. And same for I0 and I1. Okay. So that would be for this first row, Roman numeral 1. Okay. If we look at the second row, right, let me draw the OR gate here. So S is straight, and I naught is straight, but I1 is 1, so we have to negate it. Okay, so that would be the second row, and so forth, right? So we connect all inputs to their inputs of the OR gate, and then we will combine all OR gates with a second layer AND gate. All right, and here's an example for the third row. You can see that S is 1, that's why we flip it, and I naught, I1 are 0, so we keep them straight. So to summarize, for product of sum construction, for each row where the function is 0, we take their OR gate and we connect inputs to that OR gate. And the way we connect inputs is whenever that input is 0, we connect it straight. Whenever that input is 1, we invert it. And we ignore all rows where the function has the value of 1. Like here, we didn't care about those rows because we will get them kind of for free automatically. All right, so once we constructed our OR gates, we then combine the outputs of those OR gates using one big AND gate like that. All right, and if we need to write their formula, okay, we can easily do that. So that would be S plus I naught plus I1 and S plus I naught plus not I1 and so forth. Okay. All right, and is this our third quiz? I think so. All right. Here you go. So will SOP and POS work for larger multiplexers such as multiplexer 5? Yes. So the beauty of, and the reason why SOP and POS methods are worth mentioning and they're worth learning is because they are universal. Any function for which you can build a truth table, then you can apply this SOP or POS approach to find the formula. Okay, so if you start with a truth table, then SOP POS methods give you the formula, not the minimal, but it's the formula that implements that Boolean function. And then using that formula, you can use it to actually build the circuit using your gates. Yeah, SUBMIDI should be in LaTeX. Yeah, I wish I could use LaTeX on SUBMIDI, but sorry. Good suggestion for good feature request for SUBMIDI devs. All right, so now the most interesting part, the harder part is, well, what if I'm interested in using as few gates as possible? Does SOP and POS form give that guarantee that they implement the function, the Boolean function, using the minimum number of elements of gates? And the answer is no, they do not provide such a guarantee. They provide a simple translation, so it's mechanical, no thinking required, but the resulting design is not minimal, may not be minimal, so it may use more gates than necessary. And then, if we use POS or SOP, or if we're just giving an arbitrary formula, then you may want to convert this, you may minimize this formula, so change it to a different formula that implements the same function, so that you just don't have to use as many gates. And minimization is especially important because without minimization, in some cases, the designs would require dozens or even hundreds of gates. Whereas if you minimize it, you may only need a handful, like a few gates. So that is quite possible. So especially on their test, if you are asked to implement certain Boolean function using gates, and then you're finding yourself drawing like 30 gates, chances are you're doing something wrong. Chances are you need to minimize it, right? Because you would spend a lot of time drawing those gates, and maybe it will be correct, but the more gates, the easier it is to make a mistake. But more importantly, you will spend too much time. Okay, so instead you should minimize, or if it is a problem where you are asked to apply Boolean algebra laws and axioms and postulates, and minimize it by just that way, but just deriving the shorter forms of a formula, of a Boolean formula, then maybe you haven't gone all the way to the end, and maybe you can apply some rules and axioms further, and come up with with a formula that expresses the same Boolean function but uses fewer operations. So in a sense, what you do by applying laws and axioms, postulates of Boolean algebra is somewhat similar to minimization, right? Because you are applying those laws and axioms in the hope that it will make your expression simpler. Okay, and this is the same goal that you set for yourself when you use the minimization that we will discuss in a minute using K-maps or Carnot maps. If Paul 2 asking about the direct result of the SOP procedure, or is it asking about a minimized form of something? So Paul 2. This one? Well, it is asking about the circuit on the previous slide and whether you can, so it would be this, okay, and whether you can implement the same Boolean function with the same truth table using fewer than this number of gates. Okay, or maybe fewer would even mean if one of the gates had fewer inputs, that would also be more minimal, if you will, right? So if you're able to come up with a different formula that has the same number of gates, right, but each gate or some gates have fewer inputs, then it would also be better because it would be minimal as compared to the original formula. Poll number 3. Let's see. There is. Well, this is just asking about POS form, right? It says nothing about minimal. Okay. All right. So their minimization. All right, and here we are. There are three basic, the three major approaches to minimization. First is Boolean algebra, right? Use axioms, postulates, identities, lowers to reduce expressions. This is something that we have already done. Then the second method is K-maps or Carnot maps, right? Carnot is the name of the person who came up with this idea. So this is something that we will cover right now. It's a graphical technique suitable for manual minimization of relatively small circuits. So 4 or 5 inputs is doable. 5 inputs getting a little bit kind of tricky. Well, not tricky, but you have just have a good imagination to see all their different patterns. But 5 inputs is doable. Beyond 5 inputs, it's getting just way too much work. Okay, so in this case, we go with tabular methods, which we are not going to discuss in this course. So they are largely done by a program. So it's an algorithm that is suitable for large functions with more inputs. So we need to concentrate on K-maps because it has a very good illustration of the principle. It is doable by hand, and it is something that you can do without relying on any software. So definitely K-maps are going to be on our exam tomorrow. All right, and here are K-maps. So K-maps are based on their SOP, sum of products form, and their idea is that it may be possible to merge certain terms. Let's look at this example. Imagine you have this SOP formula. Can you simplify it? And well, the answer is written on the slide, unfortunately, but you would probably hopefully you can see that, well, it is this B times C term on both sides, and then, something else here. Okay. So imagine that you have the value for B and C set and fixed, and then you're just looking at changing A. So if A is 0, right, this whole first term is 0, and not A then is 1, and that means that this whole second term is BC. What if, so of course, this is one possibility, right? You have the second possibility, which is A is 1. Okay, then it means that it's 1 and something, so the result is that's something, BC, and not 1 is 0, so not A is 0, and this means that this is just 0. So it turns out, quite amazingly, that no matter how you slice it, this F is just BC. Okay, and that means that it's the same. It's a different formula, but for the same Boolean function, which means that instead of using how many gates would you need to implement this function F, given the original formula, given the formula that we have here, how many gates? Just the total count of gates. Assume you can use gates with as many inputs as you need. 3. Why? Okay, exactly. So you have, and you can start with the second layer or the first layer, however you feel more comfortable thinking about it, right? We have one operation in the second layer, right? This OR gate, and we only need one because we have one OR. Okay, and it has 2 inputs, so that means that in the first layer there are 2 gates, right? And each of them is 3 and a 3 input gate. Okay, so exactly 3 gates, and you probably need to kind of practice this a little bit so that you can see the number of gates directly from the formula without having to draw the circuit. Right? It's okay to draw the circuit; it just takes a little time, but hopefully you would with more practice you would be able to say, oh, this one is 3 gates, and it's important to kind of make this note that we in this particular case we do not count NOT as a gate, right? If we say that you should count all gates, including NOT gates, right? Then, and we know that we are only given A, B, and C straight, then you would need an additional gate to produce a NOT, okay, in this formula. So that would be 4 gates. Yeah, so with NOT gates, just look for their clues whether you should count them or not. Okay, if there are no clues, do count them. Okay, and the reason for that is because actually NOT values can be generated, pretty easily and with almost no latency in many cases, and that's why in many cases it is justified to not count NOT gates because they really don't contribute that much to the latency. Right. So and OR gate. OR gates are typically have the same latency, and it is much larger than their latency of a NOT gate. And like I said, quite often in many circuits you have already access to negated values of all inputs, and that's why it literally costs you nothing to use not A instead of A. Okay. As we were able to see, another formula that implements the same function is BC, and this is just one gate, obviously, right? So that's clearly, our SOP form was clearly not the minimal, right? The minimal would use one gate. So you could have achieved this result, F is equal to BC, from our original formula, which was this, by applying laws and rules of Boolean algebra. As an exercise, please try doing that. It is possible. However, the problem with applying rules and axioms of Boolean algebra is that there is no defined procedure, right? There's no rule that would tell you which axiom or which law to apply. Okay, you have to build that intuition. It's like with a regular ordinary algebra. You have to kind of remember all those laws and then see which one you would be able to apply to your to your benefit. And that requires intuition that is not easily formalizable. Okay, whereas K-maps are K-maps, K-map, Carnot map process is purely formal. You just need to know the rules, you follow that rules, and the result is a guaranteed minimal form of the Boolean function. Maybe not the only form, right? So there might be several minimal forms, but it is one of the minimal forms, right? So, and the reason why there are multiple minimal forms is, at least you can, convert formulas from one to another. Instead of SOP, you can use POS, for example, right? So there are multiple ways to represent the same formula. And if they both use the same minimal number of gates with the same number of inputs, then they are both minimal. So the minimal is not necessarily unique. It may be unique, but it's not necessarily unique. All right, so the graphical representation of K-maps, right? The idea stems from their Venn diagrams, and first we represent the terms in a table, and then we kind of capture the terms that we can collapse together, that we can kind of combine together. So, going back to this example, you see that, we have the same term B and C ended with A and not A. That kind of tells you that A really doesn't matter, okay? And B and C is the term that determines their output of this, the value of this Boolean function, right? So when you draw your truth table, so K-map is essentially a weird representation of a truth table. If you draw your truth table as a K-map such that A and A star values show that they do not A star, A over bar, right? Not A, show that those values do not matter. You'll graphically see it as on the K map. Right, so it's similar to the Venn diagram because we will be circling the blocks, the patterns that can be encoded as a Boolean formula using fewer letters, fewer variables than what we started with. All right, so let's do an example. First, of course, the easiest one is the two variables. Okay, well, you can do it for one variable, but that is trivial, of course. But for two variables, you build a map that looks like that. So that's what we call a K-map, right? This thing. And this is our traditional truth table. So you see a K-map is just a twisted, slightly rearranged truth table. And we have some variables here as our columns, some variables here as our rows, some variables here as our columns. And we have, with two variables, of course, the only choice is one variable is used for rows A, one variable used for columns B. You can swap A and B, it wouldn't change anything, right? Of course, if you correspondingly swap the values in the K-map. And for each variable, you list all possible values of it, right? A can be 0 or 1, B can be 0 or 1. And their value in their K-map is the value for their function at the intersection of the row and column. So this first value is for B0 and A0, right? It is actually this thing. Okay, so let's look at this value here. It is B of 1 and A of 1. Okay, so it is this row from our traditional truth table. Okay, so that's the first step. You observe the original truth table, you build the K-map, and you transfer values from the truth table to the K-map. All right, so someone is already making very correct observations. So let's do it on this slide. It's going to be on the next slide anyways, but let's do this. So exactly. Now let's look at this piece here. What it says that for b of 1, right, this entire column is for b of 1, the value of the function is 1. And it is so for a of 0 and a of 1. In other words, right, we can say, well, the value of the function is 1 if b is 1, regardless of the value of a, because for both rows that correspond to different values of a, we have 1 and 1. We have the same value for the function. So that means that our function is what? Can someone say it? Exactly, it is just b. So not even a gate required to implement this function. Whereas here we had to use 3 gates. And here 0 gates. Right? So you make this observation, right, by circling parts that have their, that have their some variable essentially eliminated, right? We eliminate a because we show that, for this highlighted, circled in red piece, a doesn't matter because the value is the same 1. The value of the function is 1, no matter whether we are in the A0 row or A1 column. Okay? How did you build the truth table? All right, let's build the truth table. Well, sometimes you will be given a truth table, sometimes you will be given a formula. So that's the formula that we were given, and you just you just go through all combinations of inputs and you determine the value of the function. So a is 0, b is 0, 0, 0, 1, 0. Okay, so obviously we have this part is 0, this part is 0, 0 or 0 is 0. We put 0 here. Okay, then next row, switch colors, I don't know, purple, right? Next row, A is 0, B is 1. A is 0, B is 1, A is 0, so it's going to be 1, and B is 1. Okay? So we see that, well, this first term, 0 and 1, it's still 0. But this second term is 1 and 1, so it's 1. 1 or 0 is 1. So it's 1. Okay? Making sense? And yes, b is the minimization of the original function. So original function was in the, our sum of products format, and we minimized it to just one variable b. Pre-input K-maps coming up. I know you can't wait. And yeah, 4 inputs and 5 inputs are even more interesting. And I think you had a 5 input K-map in the practice problem. All right. So here is the 3 input thing, right? The majority function we define as this. Okay, so this is just the formula. Please remember that you might be asked to actually come up with this formula based on their text description. Like here, imagine that you're not given the formula, but just this text description, which says that the majority function is 1 whenever the majority of the inputs are 1. Okay, so how would you build the truth table? You are told that you have 3 inputs. A, B, C, and F. All right, F is the output. F is the result. Okay, and so then you just follow the text. Do not look at the formula for now, right? So let's say you start with all zeros, okay? So it's 1 whenever the majority of the inputs are 1. Well, clearly false, right? We don't have 2, right? Out of 3, the majority would be 2. So if you have more 1s than zeros, then the function is going to be 1. All right, clearly not true in this case. 0, 0, 1. We have 1, 1, and 2 zeros, so still not true. What about 0, 1, 0? Still not true. All right, because we have 1, 1, and 2 zeros. What about then 1, 0, 1, 1? Oh, now we have 2 1s, B and C, and 1, 0. So we have more 1s than zeros. Okay, so this, according to our definition, the output is 1 because we have more more inputs at 1 than at 0. Okay, so from this truth table, you can build your SOP or POS form. Okay, and this is an SOP, right? Because it's a sum of product. So you use exactly the procedure that we covered, a few minutes ago, or 20 minutes ago. Okay, and you get this formula, SOP, sum of products. All right, and you need to build their K-map for this. All right, so how do you build the K-map? There is a very intuitive procedure. Okay, so if you know how to build their map for a smaller thing, you can just take a mirror reflection of it for an additional input variable. So here was our K-map for 2 variables, and we just flip it around this axis. Okay, so like we take this left part and we kind of make a mirror reflection. Okay, why is it a mirror reflection? Well, let's look at what we had. So we had 0 and 1 here. Okay, so initially we had 0, 0 and 1 here. So when we reflect it, we get 1 and 0, right? Imagine that like you're reflecting, yeah, and I don't know if you can see me doing this, right? You reflect the left part to the right. Imagine like you fold this slide along this line, vertical line, and initially you had something printed on the left side and nothing on the right side, and you just fold it along this vertical line so that you leave a print on the right side from the left side. All right, so it's a mirror reflection, and that's why like all the values will be mirrored. So you have 1 and 0 here. All right, and then, well, you now have one more variable here, right? So for the left part, you just take a 0 for that new variable, and for the left part, for the right part, you use 1. Okay, and that's how we obtain those values. Okay, then if you need 4 variables, what are you going to do? Well, you're going to do the same thing, but you're going to reflect over this horizontal line and add another variable here. Okay, is it making sense? All right, so for now we are at 3 variables, and those are the values. So the order shows like this is A, this is B, this is A, this is B. Okay. For 4, I'm going to show you, right? I will show you. Okay. So for 3 variables for now, okay, we just encode the truth table again. Okay. So A, B is 0 and 0, C is 0. We put 0 because it's this row of the truth table. Right? Are we good so far with 3 variables? Come on. Where's my pointer? Right here it is. All right. And one important observation that will actually help us build the K-map for 4 variables is that if you look at the progression of the values in any of the directions here and here, each adjacent value is different from the previous one, from the one to the left and to the right, exactly by 1 bit. All right, so we have 0 and we changed only 1 bit and we got 1. If we and it also wraps around. So if we had 1, The neighbor of 1 would be 0, and we can get from 1 to 0 by changing just 1 bit. All right, 0 to 1. So we change only 1 bit. Well, this is trivial because there is only 1 bit, but it's not as trivial with 2 variables and more. So we have 0, 0, and we change it to 0, 1. It's only 1 bit that we change. The set, this bit, right? From 0 to 1, 0, 1 to 1, 1, we only changed 1 bit, this bit, but we only changed 1 bit. So the rule of the K-map is that you need to make your rows and columns so that if you go from one cell to the neighbor cell, you only change 1 bit, okay, in each direction. And it also like wraps around here, right? If you have 1, 0, and you need to go to 0, 0, okay, we only changed 1 bit, this bit. Okay, so if you put, your variables for A and B not in the correct order, that would mess things up. That would not give you the right, things. Imagine you didn't reflect it correctly, and you put it like that. Okay, so then what's going to happen is when you look at 1, 1, and you think, well, how do I go from 1, 1 to 0, 0, right? Because it all wraps around. You would see, oh, from 1, 1 to 0, 0, I have to change 2 bits. Hence, my construction of the K-map is incorrect. Okay, even if in one case it is incorrect, it's completely incorrect. It doesn't matter that from here it's okay. You only had to change 1 bit, but look here. You also notice, oh, there's a violation here because you had to change 2 bits. The first and the second, you had to change those 2 bits to go to the next cell. Okay, so just pay attention to this, and if you do the mirroring properly, then you're not going to screw up. This is actually a very important observation here. It's called the gray code. So this code where at each step only 1 bit changes is very important in computer science, computer engineering, and communications, right? Because it has implications on the reliability of data transfer. Okay, so and you might have heard about gray codes, right? As a way of ensuring the integrity of the data that is being transmitted over communication networks. Okay, so this is exactly an instance of the gray code that we're using here for K-maps. All right, so with these now 3 variables, we do the same thing, and we need to, kind of circle their parts that have ones, but such that we can encode using a certain number of variables. So, like if you circle, these 3, it's not really allowing you to, just to represent it with a single expression, right? Because we see that. Right, so this is A, this is B. So we see that along the row or across the columns, we have B changes, right? B changes, it is 1, 1, but it's 0 here. But A also changes 0 and 1, 1 here, right? So we cannot do anything. So C is 1, okay? But, we cannot say that we can eliminate either A or B. So, and we cannot say that this is just, B and A, right? Because we see, well, that would be not true, right? Because for A changes, B changes, so that would not be correct. Okay, so that means, and let me erase all that stuff so that it's not confusing anyone. So you only circle the things like that, okay? So that would be, C is 1, so we put C here, okay? And then we see that A is 1 for all circled values, and B can be 0 or 1, it doesn't matter, okay? Because whether B is 0 or 1, the value is the same, so we can eliminate B. So this is our first term. And then you do the same thing here, right? You circle like that. What would that be? Well, here C doesn't matter because C is 0 and 1, right? For C can be 0, C can be 1, doesn't matter. So it means that we have A and B, right? And similarly, third, you can circle this one, okay? So this one, the third one is C is 1, and we are looking at B. B is the same, 1, and A is changing. So A can be 0, A can be 1, it doesn't matter. So we got this expression, okay? So the number of cells that we are circling must be a power of 2. But remember, you have to think, you have to think about wrapping this, right? So this may wrap in this direction, and this also wraps in this direction, okay? So it's almost like, like a sphere if you have good imagination, right? So you have to look at how this thing wraps along both dimensions into, some kind of three-dimensional structure. All right, so here is the example for that we just went over, okay? So, and we are merging. So basically, I explained how this merging works, right? If C is 1 and B is 1, it doesn't matter what the value of A is, and that's why we can, eliminate A altogether and just get, B and C from here. All right, so if we just follow all the reductions properly, I think that's the same result that I got. CA, BA, CB, CA, AB, and CB. Yep, so the reduced result is the same, and it is guaranteed to be their minimal formula. Okay, it may not be unique, but it is guaranteed that there is no other formula that would use fewer gates. And another example, this one is easy, right? Here we were able to circle 4, and now we can actually do the formula, right? So C changes, so it doesn't matter. And then A changes, so that doesn't matter. And B is at 1 for both cases, so this is just B, okay? So we were able to eliminate 2 variables out of 3 for this formula. So this is just B, okay? And you can do this, all right? So your 4 may be placed like that, okay? So you can do that. And obviously here, F is just C because both A and B change, all right? And C is 1. So hopefully you see their kind of rule, right? If we have 4 ones here, like that, it means that we were able to eliminate 2 variables, right? If we have any block of 4s, like here, it would mean that we were able to eliminate one of the variables, all right? A, B, or C. All right, and here's an example with wrapping, right? So this wraps in this direction, and it's still 4, okay? So that means that our function is not B. Why is it not B? Because we see, well, C doesn't matter, it changes. And then A changes, it's 1 and 0, so it does change. And then B is at 1, so it has to be negated when we take it for this formula. Okay, so as we mentioned, K-map, this concept is only for a relatively small number of variables. 4 or 5 is probably the limit, and there are there are other methods for more variables, right? And most of them cannot be done manually. All right, so and then we have 2 minutes left, so let me show you how you can do 4 and more variables. And I have a very good resource that I personally like very much to show you. And it's this allaboutcircuits.com. And here if we look at their examples, no, that's not it. All right, for 4 variables. All right, here it is. So you see that we basically took our 3 variable thing and reflected it towards the bottom, and we just reflected. That's why you see this 0, 1 became 1 and 0 because we reflected, and then we took, since we added a variable, so we took it for 0 in the original half that we already had, and then we took it as 1 for this reflection, mirror reflection that we just did. Okay, and you can do that for 5 as well. So see here, we reflected again from left to right. We did a mirror reflection from left to right, and again we took the mirror reflection. So we have 1 0 in the end here, 1 1 0 1 0 0, and then we just added the first bit for the new variable. Okay. All right, it's 1:50 on my clock, so maybe it's not well synchronized, but forgive me. I will check it. Thank you, folks, and yeah, please, if you can join us for the review session tonight, and make full use of your review session on Wednesday with lab TAs and mentors, and enjoy the rest of your day, and good luck on the exam tomorrow. All right, thank you.